Okay, so today is actually a really exciting lecture. Today is one of the, today is where we stop being children who just study free quantum field theory and we become adults, okay, who study interacting quantum field theory. And in particular, so last class we introduced the method of path integrals, which is a very convenient way for understanding how to compute observables in quantum mechanics. And let me just remind you of how that worked. So in quantum mechanics, let's say that you had, let's just say sorry, that's a little bit messy. Let's just say that you had a particle that started at some initial time t initial and ended up at some final time. So you start with a particle at position q initial at time t initial that ends up at a position q final at time t final. And then if you want to study the matrix element of some observable, the expectation value of some observable for a particle that starts and begins at these locations, then we learned last time that the way that you can compute this expectation value is to perform a path integral where you integrate over all paths between the initial and the final location of the particle, weighted by the classical action. So the classical action is sort of like the measure factor in this integral. And if you want to compute just a transition amplitude, so with none of these factors here inserted, then the amplitude for a particle to move from one configuration to another is just given by an integral of this measure factor, e to the is. But if you want to compute an expectation value, the sort of thing that you might actually measure in quantum mechanics, then you would insert the location of the particle at these various different times in the path integral. So, for example, if you're doing a double slit experiment and you don't want to compute the amplitude to propagate through the slit, through the one of the two slits, then you would perform a path integral of this sort. But then if you wanted to measure the location of the particle, say which slit it goes through, then you would insert an operator q, or insert the position of the particle q inside this path integral. So just as a reminder, because it will help sort of establish something that we'll be using in just a minute, one could also view this not as a path integral over the possible locations of the particle q, but you could also view this as an integral over phase space. That is to say, an integral over all paths that the particle could take through phase space rather than through physical space. And in that case, the integrand is actually precisely the same. It's the integral of the action, but it's the action written in Hamiltonian form. So you think of the action not as the integral dt of a Lagrangian, but as the integral dt of something that's a function of p and q, and in particular is this usual phase factor. So remember that this is otherwise known as the Lagrangian, expressed in terms of p's and q's, so pq dot minus the Hamiltonian. And at the end of, so this is the standard path integral formulation of quantum mechanics. And at the end of class last time, I introduced a little trick which allows us to, instead of computing transition amplitudes, to compute correlation functions in the vacuum state. And the way that we compute correlation functions in the vacuum state is we really use a very sneaky sort of trick, which requires us to observe that if you just took any state in a quantum theory, and instead of acting with the usual unitary time evolution operator, we inserted a small imaginary part here. So instead of acting with e to the iht, we act with e to the iht times 1 plus a small imaginary part, then at very late times, this has the effect of just projecting the state onto the vacuum. Sorry, I guess that's at very early times, right? Because what is the idea here? The idea is that you have an I epsilon here, which becomes minus epsilon t, which at very late times becomes, or at very early times, becomes e to the epsilon times a very large negative number times the Hamiltonian. And if you have any state, and it's only the lowest energy state that will give the dominant contribution at very early times. Similarly, if you acted with this operator on a bra vector from the left, you would similarly just project onto the vacuum state at t goes to plus infinity. So this is, it's a bit of a sort of nasty technical trick. But what it means is that if you are only interested in computing correlation functions in the vacuum state, then in fact life is very easy. Because all you need to do is you need to modify this path integral so that instead of performing an integral dt, you just do this slight change of variables where you replace t with t times 1 minus I epsilon. So 1 minus I epsilon. Or actually, let me say that a little bit better, because really what we're doing is we're replacing the Hamiltonian by 1 minus I epsilon times the Hamiltonian. So I'll write it this way. 1 minus I epsilon times the Hamiltonian. And then we have our q of t1 to q of tn. So effectively what we're doing here in this term is we're adding a small imaginary part to all of the energies of states in the theory. And what that means is that this effectively projects us onto the vacuum state. So this is a handy little trick that will allow us to never have to worry explicitly about what the actual functional form of the ground state wave function, say, is when we're studying quantum field theory. In quantum mechanics, of course, you could just compute the ground state wave function explicitly if you were doing, for example, the harmonic oscillator. But even if you were studying in quantum mechanics any more complicated theory, the anharmonic oscillator or something with a non-trivial potential, the form of the ground state wave function would be very complex. And this, at least formally, gives you a way of avoiding any subtleties about how to compute the ground state wave function. For the time being, though, if that factor of epsilon confuses you, just don't worry about it, because it's not actually going to enter into there's essentially no computations we'll do this semester where it'll enter. When you do loop computations, it'll become a bit more important. But for now, it's something that is a subtlety that you don't have to pay too much attention to. Yes?
Why do we always take correlation functions with respect to the ground or the vacuum?
Well, there's no rule that says that you have to take correlation functions with respect to the vacuum state. If, for example, you were computing a scattering amplitude, as you might do in a particle accelerator, then that is the sort of thing that you would do, okay? Because you might want to calculate, say, the probability for two particles to scatter off of one another in vacuum, or the probability for one particle to decay to some other collection of particles in vacuum. But there's certainly no reason why you couldn't study these correlation functions in other states. So, for example, if you're studying materials physics, you would probably want to study this at finite temperature. And there is a whole, there's a whole course here on finite temperature quantum field theory, right? Which develops techniques to compute these things at finite temperature. In general, the techniques that people use are very similar to the techniques that we'll be using today, but it is a bit more complicated. So there's really no, the reason why I'm focusing on the vacuum state here is because it's the simplest thing, the thing that we're usually interested in, but it's certainly not the only thing that we might be interested in. Other questions? Good question. It turns out that for the case of finite temperature physics, there's a beautiful way of modifying the path integral description that I've introduced today to account for the fact that you're at finite temperature. It's something that I would love to teach, but it's not something that I did, at least in the past, because I didn't have enough time. But there's always hope springs eternal. Any other questions? Great. Okay. So the important thing that I want to emphasize with this equation really is that I had to say proportional to rather than equals to in this expression, in part because I've neglected these normalization factors here. Okay. So if I wanted to have an equality rather than a proportional to symbol, well, there's a couple things that I could do. One thing that I could do is I could just try and compute those ground state wave functions explicitly and then compute the overlap with whatever state that I'm interested in. But a much cleverer thing to do is just to use the fact that we want our vacuum state to be normalized, so that the norm of the vacuum state should be equal to 1. And if you think about it, all that means is that we just need to modify this so that we divide out by the contribution in the vacuum. So this denominator here is just here to keep the vacuum state normalized. If you like, you could think about first computing the unnormalized quantity, where I don't have that denominator, and then dividing out by the norm of the vacuum, okay? Dividing out by the path integral with no insertions of Q, just as a way of ensuring that the vacuum state is normalized. And this is really the basic formula that we're going to be using. And in particular, it's kind of amazing. Like, this formula, as I've written it, appears incredibly abstract, right, and not particularly useful. It says that if I want to compute a correlation function in the vacuum state of any quantum mechanical system, then I have to integrate over all paths through configuration space that the quantum mechanical system will take with some insertions. And it's not at all clear how you would actually use this formalism to do some calculations. But it turns out, and as we're going to see today, that it really is not very much work to turn this into a very efficient and practical tool for calculating these correlation functions. I mean, it's sort of remarkable. I mean, from this point, we're only about 45 minutes away from deriving Feynman diagrams. But maybe before we get to that, I should just pause and see if there are any questions. Maybe just to put this approach that I'm describing today in context, if you look in your textbook, this is not the approach that Peskin uses to derive Feynman diagrams. I think this might be how Srednicki proceeds. If you look in your textbook, the Feynman diagram derivation using path integrals is in there, but it's buried much later in the book, around chapter 9 or 10. So it's probably worth, just for your own education, reading through Peskin's derivation of Feynman diagrams using a more canonical approach and comparing it to the derivation that I'll present today and next week, or in next class. Okay, well, first things first. So here I've written down the formula for the computation of some correlation function in quantum mechanics for a single degree of freedom that I called Q, which could be the position of some particle. It's straightforward, I hope, to see that if we want to generalize this to many degrees of freedom, let's call them Q sub I, then what do? Well, we just integrate over all paths that those many coordinates could take through configuration space. So, for example, if you have a particle moving in 3 dimensions, then I could indicate label the x, y, and z locations of the particle. Or if you have some sort of many particle or many body system, the I could run over the locations of many different particles. Or if you think about our simple mechanical model of a field theory, where you have your degrees of freedom being the vertical locations of some balls connected by some lattice of springs, then each Qi could label the location of one of those different balls. And in a quantum field theory, where the dynamical variable is some sort of local degree of freedom, which in a scalar field theory we would call phi, this path integral prescription then says that we should compute a expectation value or a correlation function in quantum field theory by integrating over all possible paths through configuration space. That is to say, over all possible field configurations phi of x. And so our goal today is to develop an algorithm for computing these things. In particular, what we want to compute is the expectation value of a bunch of field variables. And for the sake of simplicity today, we'll just be talking about scalar fields, although we will be able to, in short order, generalize this to other sorts of fields, such as spinors and vectors. And we're going to compute this correlation function by computing this field theory path integral. So I'm now going to present a technique that will allow us to compute this. But before I do so, let me pause and see if there are any questions. Yes? Oh, I'm sorry. I accidentally moved to Euclidean sigma. Yes, sorry. Sorry about that. That's an I in the denominator. Yeah, very often we use this trick that I mentioned last time where we take t to it, which has the effect of removing that I from the action. So sorry, I sometimes accidentally write e to the minus s because that's what I'm thinking about in my head. But of course, we're just going to be using e to the is. Yes?
Just remind me, when we doing path integral, integrating all into continuous paths, and do they have to like slower than light or something?
That is a great question. Okay. That is a great question. Okay, so the question is exactly what sort of paths we integrate over. So the first thing that I should point out is you might ask, do we have to integrate over continuous paths, or could the path be not smooth or something like that? You know, could the derivative of the function, does the derivative of the function q have to exist, or the second derivative, or anything like that? The short answer is that we don't really know precisely how to define a path integral, so I can't give you a precise answer to that question. In particular, as you're going to see, we'll only be able to define this path integral precisely in an approximation around a case that we can solve exactly, which is the free theory, which I'm going to compute for you momentarily. And as you'll see, implicitly in my calculation, I'll make some assumption about the smoothness of the path, actually. In particular, what I'm going to assume is that the path has a Fourier transform, which is sort of nice in some sense. The second question that you ask is much more interesting, though, is do we have to integrate over only, say, those configurations where a particle is moving less than the speed of light? And the answer is absolutely not. We do not impose any constraint like that. Remember, the whole point, so why does a particle move less than the speed of light? Okay, it moves less than the speed of light because it has to solve some equations of motion that are consistent with special relativity. The entire point and the magic of the path integral prescription is that it, you don't restrict yourself to classical solutions of the equations of motion. And in particular, that means that there's a sense in which you have to integrate over paths where the particle is traveling faster than the speed of light. And so you might worry then that there's some tension between this and causality. Okay? But the magic of causality is that even though at intermediate steps in the calculation, it may appear that the particle is going faster than the speed of light, in the sense that there are virtual paths or contributions to the total integral where the particle is moving faster than the speed of light. The magic of special relativity guarantees that the answer at the end of the day is going to preserve causality. For example, we're going to compute a two-point function using this path integral approach. We're going to do it later this class. And we're not going to impose causality, we're not going to restrict the path integral at all to only include particles that move slower than the speed of light. But the answer that you get for the two-point function is going to be the same answer that we derived when we quantized the free field theory directly. And as we saw, because the commutator vanished outside of the light cone, it was impossible to send a signal faster than the speed of light. The correlation function between two field operators was non-zero outside the light cone. That meant that the value of these observables that are causally separated are correlated with one another. But correlation is not the same as causation. Okay? That's as true in physics as it is in all the other scenarios where someone says that phrase. Yes.
So is there a way to obtain these to the minus 10 effective distance?
Absolutely. Yeah.
How would that be?
Well, you need to think about it as a saddle point contribute, right? Remember that a good way of approximating an integral is as a saddle point. And so you need to find what the saddle point is. The saddle point is, roughly speaking, a solution to the equations of motion. And so what you need to do is calculate the action for a solution to the equations of motion. But it's a slightly subtle solution to the equations of motion because it's one that's outside the light cone. So it's a slightly artificial one, but you can actually do it. Good. Other questions? Okay. Okay. So in order to compute this object, I'm going to start with a little trick. Okay. So in particular, I'm going to define what is known as the partition function. Or, more properly, it should be probably called the generating function. Of a quantum field theory. And it's typically denoted z. And it's a function of another variable, j, that I'll call a source. And it's defined as follows. It's defined as the integral over all field configurations of this usual measure factor that appears in the path integral plus a source term that couples your field phi to that function j. So right now, this is just a definition. Okay? I haven't actually done anything yet. One of the things that I should note is that there's a reason why I call this j a source term. Because if you were to compute, for example, the classical equations of motion that would, for the field phi, would arise if we included that extra term here in the action, that would give you a source j that would sit on the left-hand side of, the right-hand side of the field equation. So, for example, the Klein-Gordon equation would tell you that your scalar field now has a source term that sits on the right-hand side. And indeed, if you remember the formulation of electromagnetism in quantum field theory, we had that A mu J mu term, which described how an electromagnetic field responds to a source in Maxwell theory. And if we wanted to, we could expand out that exponential, the e to the I integral of j times phi. And what would you get? Well, you would get 1 plus I times the integral of j times phi. And then you would get another term, which would be a minus d4x, d4y, j of x, j of y, phi x, phi y, and so on and so forth. So there would be an infinite number of terms that you would get by expanding out that exponential. And what I want you to do is I want you to just look at the various terms that appear in this generating function. And I want you to note that the term that is, say, linear in J is exactly what you would want to compute if you wanted to compute the expectation value of 1 phi. And the term that is quadratic in J is the thing that you would need if you wanted to compute the correlation function of 2 phi's, the 2-point function of phi. The term that's cubic in J is exactly what we would need to compute the 3-point function, the correlation function of 3 phi's, and so on and so forth. So this partition function includes the data about all possible expectation values of the field that you might be interested in computing. So we're going to momentarily compute this partition function in a free field theory. But before we do so, let's just ask ourselves how, given this partition function, we would go about actually extracting from it one of the correlation functions that we're interested in. So, roughly speaking, what we saw is that, say, the term that is linear in J has 1 phi, and if you wanted to extract the term in Z that's linear in J, what would you do? You would take the derivative of Z with respect to J and then set J equals to 0. And indeed, that is exactly what we're going to do. The only slightly subtle thing is that J is itself a function. So when I say take the derivative, I really mean take a functional derivative. And so we can just define the functional derivative as follows. So if you have something that depends on J at a particular point y, then we declare that the derivative of J of y with respect to J of x is a delta function that sets x equals to y. Now, at first sight, that expression might look a little bit confusing, but if you really just think about the analogy with finite dimensional derivatives, where you would be taking a gradient, and you think of x and y as an index that labels different variables for some multidimensional gradient, then you'll see that this is just a variant of the usual statement that, say, if you've got a bunch of variables, say qj, and you want to take the derivative of qj with respect to qi, this would be delta ij. Okay. Indeed, I believe in one of the problem sets that you're doing on Friday, you'll verify explicitly that this functional derivative is nothing more, nothing less than the usual derivative of multivariable calculus. So this is the functional derivative of J. And then the idea is that more complicated functionals, or more complicated derivatives, are then defined using this formula and the chain rule. So, for example, if you have some function v of phi, then where phi is a field, then the variational derivative of v with respect to phi of x is v prime at phi of x. Where prime here is just the usual derivative with respect to phi. Or, for example, if you have an action which is a function, an integral of a Lagrangian, that's a function of phi and phi and its derivative, this is just the usual Euler-Lagrange equation. Evaluated at the point x. Are there any questions on this? I mean, sometimes in a classical mechanics course, people see variational calculus. I mean, I know you see variational calculus in your classical mechanics courses. You don't always think about it terribly carefully, and you often think about delta phi as some formal variation without thinking about a variational derivative in some precise sense. All I'm doing is trying to make this variational derivative precise here. And really all you need to do is remember this expression here and the usual chain rule of calculus. Actually, I suppose I was a little glib here. There should be a phi of y and a delta 4 of x minus y. Sorry about that. Good. Any questions? Yes. Mm-hmm. Oh, I'm sorry, minus a half. Thank you. Good. Excellent. Okay. So remember, so now we just need to put these two things together. So the partition function is the integral of the action with the addition of a source term so that means that if you want to compute the vacuum expectation value of your field, what do? Well, you just need to take a bunch of variational derivatives of your partition function. In particular, if you want to compute an endpoint function, you'll need to take n partial derivatives and then set j is equal to 0. And there's a factor of I right here, so we should really divide out by that factor of I. So I'll put a minus I to the n. And finally, I need to normalize this thing by dividing out by the path integral with no insertions. And that's just z at j equals to 0. So if I can compute this path integral for the generating function, then all I need to do is take some derivatives of it in order to extract the correlation function. Any questions on that? One thing that sometimes confuses people and is important to bear in mind is that the locations of the positions here of the different field operators phi is reflected by the locations where we insert these sources. Any questions on this? Is this all clear? So let's just do this all very explicitly. And let's check that we can reproduce something that we already know. So let's do the example of a free scalar quantum field theory. So in this case, we have a single field variable phi. And the action is minus 1/2 integral d4x of d phi squared minus m squared phi squared. But what I would like to do, just to make things a little bit easier, is I'm actually going to integrate that action by parts. Okay, you can always write d mu phi as a total derivative times phi d mu phi. I'm going to do that just in order to make everything look a little bit more symmetric. So that tells us that this partition function, what is it, just to write everything out in its full glory, it's the integral of the exponential minus I over 2 integral d4x phi of x d squared plus m squared times phi of x. And then we have the source term, which is I times the integral d4x j of x phi of x. So, in order to think about how we might do this integral, let's just think about the overall structure of that integral for a second. And let's forget about the fact that we're doing an infinite dimensional path integral, and imagine that we were just doing a finite dimensional integral. Let's just pretend that phi was a single variable, for example, rather than an infinite number of variables. Then, if phi were just one variable, this would just be a quadratic Gaussian. This would just be a Gaussian integral. It would be an integral that looked like the integral d phi of something that looked like the exponential of phi times a phi, okay, where a is the analog of d squared plus m squared, plus j times phi. Okay. So that's schematically what you expect the integral to look like. And everyone can do a Gaussian integral, right? In my case, that's just about the only integral I can do. But how would we do that integral? Well, one way of doing that integral would be to shift phi to complete the squares. And what answer would you get? You would get something like j a inverse j. Well, j squared times a inverse, but I'm writing that as j a inverse j for reasons that'll become clear in a little bit. And in particular, the reason why I'm writing it as j times a inverse j is that if you wanted to have, say, a multi-dimensional integral rather than a single-dimensional integral, where phi now has an index, okay, we could call it I if we wanted to, then this would be some sort of matrix, aij, and then this would be, the A inverse here would be the inverse of that matrix, aij. So I guess we would. And then you would contract that inverse matrix with the vectors j. So I've only written a squiggly line here because on your problem set this week you'll actually compute this integral explicitly. But the important point that I want you to think of is that I want you to think of our discrete model of a quantum field theory where you have one field variable for each point in space, and you imagine now that space is discrete. And then that means that this path integral that we're doing up here is really a finite dimensional integral, where you only have a finite number of variables, phi at position x1, x2, x3, and so forth. And then this operator here is really just like your matrix A. And so what this means is that you should expect this path integral to be something like j times the inverse of that kinetic term, d squared plus m squared, times j. Now, if you've been paying attention, earlier in this class, we already met something that was the inverse of the kinetic term. Does anyone remember what it was? It's the Green's function. It's the propagator. So we already have a guess for what this generating function in a free quantum field theory should be. What I would like to do, just to make this all very explicit, is just go ahead and compute that integral over all field configurations phi completely explicitly. So to actually do the computation, what I would like to do is, in fact, use the Fourier transform, because one of the things that we learned is that this kinetic operator, d squared plus m squared, if you think about it as a matrix, is a diagonal matrix in momentum space. Well, what do I mean by that? Let's see. So what I want to do is take our field variable phi, and instead of thinking about the field variable in position space, I want to think about it in momentum space. So this will be the integral of e to the minus ikx times some function phi tilde, which is the field variable in momentum space. And what I want to do is I want to change variables. So I want to think about my path integral not as an integral over all configurations phi of x, but over all possible Fourier components phi tilde of k. Okay. So I want to take the integral d phi of x, and what I want to do is do a change of variables, just like you would do a change of variables in any old integral, to think about it as an integral over phi tilde of k. What do I mean by that literally? Well, let's just imagine that we had this integral over over d phi x, the integral over possible field configurations. You could really think about that as a product over all values of x of some normal one-dimensional integral, d phi x. That's all that we mean by a functional integral. And I'm just doing the change of variables, where now we have, the integral over all momentum modes, where I'm just doing a standard one-dimensional integral over all possible momentum modes. Now, you might worry that whenever you do a change of variables in calculus, you have a Jacobian determinant that arises when you do that change of variables. Indeed, the Jacobian determinant is not actually too hard to compute in this case. This is a linear change of variables. We're going to phi to some linear combination of phi, where those linear coefficients are just these e to the ikx's. So that means that if you wanted to compute the Jacobian determinant, it's just the determinant of some matrix. Okay, now it's an infinite by infinite matrix, but it's got a determinant nonetheless. But the point is we don't actually care about that, because that's just some overall normalization in our path integral. We're going to divide out by that at the end of the day. There are other sort of more subtle arguments that we might make later on when we quantize gauge theories. where we'll actually care about determinants that appear when you do changes of variables in the path integral. But for now, I just want you to think about this as some overall constant contribution to the path integral. Okay, so our path integral is now viewed as an integral over possible Fourier modes of the field phi. We just need to ask what the integrand looks like when we write it in Fourier space. Any questions before we work that out? So what was the integrand? So it was an integral d4x of phi of x d squared plus m squared phi of x. So we just need to go ahead and think about our field in Fourier space. So that's now an integral d4k, integral d4k prime, where I've introduced two Fourier variables k and k prime, of an e to the minus I kx times phi tilde of k, and then a d squared plus m squared times an e to the minus I k prime x phi tilde of k prime. And then, and then there was an integral d4x, integral d4x. We can then use that integral d4x. So it's an integral d4x. So first of all, what we want to do is use the fact that this d squared plus m squared becomes a minus k squared plus m squared, right? Because it just acts on the e to the I k prime squared plus e to the minus I k prime times x. So actually, I suppose you should say that that's a k prime squared plus m squared. But we also want to use the fact that when you do the integral d4x, you get an integral d4x of e to the minus ix times k minus k prime. That's a delta function that sets k equals to k prime. So you can use that to do the k prime integral. And you get an expression for the kinetic term of the action in momentum space, which is an integral d4k phi tilde of k times minus k squared plus m squared times phi tilde at minus k, because k prime was equal to minus k. Right, this is the advantage of working in Fourier space. Okay? That d squared minus m squared, which was some horrible differential operator, becomes just a function of k. This is what we mean when we say that that kinetic term, it looks like, is the analog of a diagonal matrix in momentum space. If you think about the infinite by infinite matrix, whose columns and rows are labeled by k, then it's a diagonal matrix as thought of as that infinite by infinite matrix. So let's just go ahead and write down our expression for the generating function. So in order to do that, actually, first, let me just so I'll just note that we also had the source term that appeared in the generating function. So similarly, I'm going to write this in terms of the Fourier components of phi, as well as, yes, question?
Why is k prime equal to minus k?
Ah, good. So when I do this integral, I have an integral d4x with an e to the minus ix times k minus k prime. And what is that? That is a delta function that sets k equals to minus k prime. Okay, sorry, with the plus there. So that delta function I can then use to do the k prime integral, and that sets k prime equals to minus k. Good question. Any other questions? Okay, so we can now write out the source term using exactly the same trick. So it'll be an integral d4k times the Fourier component of j times the Fourier component of phi. And we can then go ahead and use that to write down a full expression for the partition function. So now it's an integral over all of the Fourier components of the field phi of an integrand, well, we had an I over 2 times that kinetic term, which was a d4k of phi tilde of k. So there was actually a minus sign, hopefully. Let's take a look here. Yes, so there was a minus I here. So that minus sign gives you a k squared minus m squared times phi tilde of minus k. And then you get the source term. So that source term was I integral d4x, j of x, phi of x. And I'm actually going to write this as the sum of two terms just to make everything a little bit more democratic looking. I'm going to write this as the integral 1/2 times the integral d4k of j tilde of k, phi tilde of minus k, plus the same thing with k going to minus k. So you can easily see that that's true. All I've done is divide that integral into two pieces and do the change of variables k to minus k on those pieces. But that makes the integral look a little bit more symmetric. So I get a j tilde of k, phi tilde of minus k, plus j tilde of minus k, phi tilde of k here. But remember that you really want to think about that integral over all momentum modes as just a product of a bunch of one-dimensional integrals. And you see here that the integrand here, it completely separates. The different k modes just don't talk to each other. You know, so this is the advantage of thinking about this in momentum space as opposed to position space. In particular, what is this? This is just the product over all the different momentum modes of a bunch of one-dimensional integrals. So what do you have? You have the exponential, just rewriting this, of a one-dimensional integral just rewriting what we had here. Sorry, there was no I there. And now this is a one-dimensional Gaussian integral. And we all know how to do one-dimensional Gaussian integrals. So in particular, one easy way to do this one-dimensional Gaussian integral is just to complete the squares. So in particular, let's just define some new variable. I'll call it chi, where what have I done? I want to shift phi by adding something proportional to j over k squared minus m squared. So let's just go ahead and see what happens when I make that shift. So we get product over all momentum modes. Now, instead of doing the integral d phi, I want to do the integral d chi. That's just a simple change of variables. I've shifted my integration variable by a constant. So that doesn't do anything. I can just go ahead and do an integral d chi. And what's the thing that I'm integrating? It's I over 2. What do you get? Let's see, you get a chi of k times a chi of minus k times that kinetic term, k squared minus m squared. And I chose this coefficient here so that if we went ahead and write it all out, there'll be no terms that are linear in chi. But I do that at the price of introducing another term here, which is j of k, j of minus k over k squared minus m squared. Right, if you just went ahead and plugged this expression for chi into this expression up here, what would happen is you would get this term right here from the term proportional to chi squared. The terms linear and chi cancel by design, and you're left with something quadratic in J. So now if I wanted to, I could go ahead and just do that chi, the integral over the chi's. Yes, question.
Okay. So in the various integrals, where does the k squared minus m squared come from?
That is the kinetic term, right? So this derivative, so remember the action? Good. So the action here is d squared plus m squared times phi. When you go to Fourier space, that becomes a k squared plus m squared, because d squared plus m squared of e to the I kx is k squared plus m squared. And then we're just carrying it through the various different terms here. That's an important point. It's just the kinetic term.
Why is there a sign change?
Oh, is there a sign change? There was a minus sign somewhere, because there's this minus sign right here. So that's why you got a k squared minus m squared instead of minus k squared plus m squared. Because, yeah, just to make that totally clear, because you have an I here, that d squared becomes minus k squared. Good questions. Okay. So, what is z of j then? Well, you could do the chi integral if you wanted to. But the point is that it almost doesn't matter because it's completely independent of j. So whatever it is, it's just z at j equals to 0. The j dependence just comes from the second term, which is the integral d4k, j of k, j of minus k, over k squared minus m squared. So here we've written our answer for the partition function of a free field theory in terms of the Fourier transformed variable, the j tilde. If you wanted to write this in terms of the original variable, you should do the Fourier transform back. So you should let j of k be the integral d4x e to the minus I kx, j of x. And what will you get? Well, z of j is then just some constant times the exponential of 1/2 integral d4x integral d4y of j of x times j of y times a function of x and y that I'll call delta, or maybe I called it d. I think I called it d earlier. Let's call it d, where what is d? Well, it's the integral d4k of e to the I k x minus y. Just plugging in, coming from this integral d4k of e to the I k x minus y. The e to the I k x minus y coming from these two phase factors here times I over k squared minus m squared. Okay, magic, we've derived the Feynman propagator. So this is the Feynman propagator. In fact, If you remember what I taught you earlier in this course, I said if you want to be very careful about being in the vacuum state, then you should have included that I epsilon in the path integral. What did that I epsilon do? It was effectively adding a small imaginary part to the Hamiltonian, or effectively adding a small imaginary part to the energy. What is the energy in this expression? Well, the energy is precisely the denominator of this formula. So if you went through all of the details carefully, you would actually have a little I epsilon there. And in our derivation of the Feynman propagator, we used that I epsilon as a clever trick for keeping track of which poles we were including in a contour integral. Here you can see that I epsilon arises as a consequence of demanding that we're in the vacuum state. But in any case, I hope you sort of appreciate what we've done here, which is we did a path integral derivation of a generating function that includes in it all possible correlation functions in a free conformal field, free quantum field theory. So, for example, let's imagine that we wanted to compute a two-point function. So here, of course, we're computing the time-ordered two-point function, which is the thing that path integrals do for a living. Well, let's just look up at our handy formula up here. We just need to take two derivatives of this partition function with respect to j. And we had a minus I squared out front. So what is that? Well, there was a minus I squared over z of 0 times the second derivative of our partition function. And in order to compute the second derivative, what do we need to do? Well, we just need to start expanding out that exponential in our expression for the generating function. So we have the exponential of this quantity in the parentheses here. So that's 1 plus, we got a 1/2 there from this factor here. And then you get an integral d4x, integral d4y of j of x, j of y, d of x minus y, plus higher order terms, all evaluated at j is equal to 0. Now, I don't need those higher order terms, because if I only take two derivatives with respect to j and then set j is equal to 0, all the terms in that expansion of order j to the 4th, j to the 6th, and so forth will just be equal to 0. And so now I can just go ahead and compute that using the fact that, say, the derivative of j of x with respect to j of x1 is a delta function that sets x equals to x1. So what is that two-point function? Well, if you take the derivative of that guy, it's just equal to 0. Actually, I left out, there was a z of 0 here, which cancels this z of 0 right here. So I'm just going to cancel it out. I hope there's no I that I'm missing here. Okay, well, it's possible there's a sign mistake somewhere.
I think it's supposed to be minus 1/2.
Is it minus 1/2? Is there a minus here? Is there supposed to be a minus there? Is there a minus there? Yeah, that better. It has to be a Gaussian with the right sign. So I think there's a minus there. Good. Perfect. So that's going to cancel the minus sign that comes from squaring this guy. And then you have a 1/2. But the point is that there's two different ways of taking this derivative. This d by d j of x1 could act on j of x, or it could act on j of y. And same for that d by d j of x2. So what you're left with is two different factors, both of which just give you d of x minus y. So this reproduces the calculation that we did using free field theory for the time-ordered correlation function of two of these field operators. In fact, this gives a more general result, which is a general result for any free quantum field theory, which is that if you want to compute the vacuum expectation value of a bunch of these field operators, well, how would you go about doing that? Well, let's just stare at this expression here for z of j. Well, if you expanded that out, you'll only ever get terms that are quadratic in j. Okay? So that immediately tells you that any correlation function between a bunch of free fields, it's going to vanish unless you have an even number of fields. And what is it going to be? Well, it's going to be a product of a bunch of propagators, a product of a bunch of d's. And if you stare at it for a minute, you can hopefully convince yourself. And I suppose there's a little argument that goes here, which I'll leave it to you for an exercise if you're interested in. But hopefully you can sort of see it that it's morally true from this formula, that just what you get is a sum of a bunch of products of free propagators. And you have to sum over all the different ways that these propagators can be matched up together. So that, for example, phi of x1, x2, x3, x4 is going to be equal to the propagator for a particle to go from x1 to x2 times the propagator to go from x3 to x4 plus the propagator to go from x1 to x3 times the propagator to go from x2 to x4 plus the propagator to go from x1 to x4 and from x2 to x3. So hopefully from our expression for the generating function, it's clear that the answer that you will get is a product of a bunch of propagators. And if you think about it, the only thing that sort of makes sense is if it's just a product of sum over all different ways that you could match the points together. And then it's some sort of straightforward combinatorics just to convince yourself that that's indeed really true. And this is a result that is known as Wick's theorem, which is the statement that a general correlation function in a free quantum field theory is just a product of a bunch of free propagators. Yes?
What happens if you have like three of the terms in your expectation value instead of a given number?
Well,
You don't look like you have any doubling up of that.
yes. So what happens? What is the three-point function of a free field? So let's just imagine doing that in two different ways. So let's imagine that you wanted to compute, say, this correlation function. Well, let's first imagine we wanted to do it using the raising and lowering operators. Well, each one of those phi's has one raising and one lowering operator. But if you think about it, those raising and lowering operators need to be paired in order to get a non-zero answer. So from that point of view, you can already immediately see that that three-point function is 0. And if you look up at our expression for the generating function, it's the exponential of something quadratic in j. So if you expand it out, you only get even powers of j. So that means that you get only terms in this expansion that give you even correlation functions. In fact, there's a symmetry. For the free field theory, there's a nice symmetry that guarantees this fact. Can anyone see what that symmetry is? So if you take phi to minus phi, the action is invariant. And so the correlation, and indeed the vacuum state respects that symmetry, which means that the correlation functions must obey it as well. And anything that involves a product of an odd number of phi's will not respect that symmetry. So, for example, that immediately tells you that if we were studying phi to the 4 theory, then you would also have all of the 3-point functions and 5-point functions and so forth vanish. But if you were studying phi cubed theory, you would not. Okay. So, what I would like to do, so are there any more questions before I continue? Yes. No. Just scratching yourself. Any other questions? Okay. So, what I would like to do now is just introduce a sort of suggestive notation. Because I get tired of writing formulas. So, in particular, what I want to do is I want to introduce a graphical notation to keep track of all of the terms that are appearing in this sum. In particular, we have this expression for z of j. What was it? It was the exponential of, I believe, minus 1/2 times the integral d4x, d4y, j of x, d of x minus y, j of y. I would like to introduce a notation where every time I have an integral d4x, j of x, I want to represent that by a dot with a line connected to it. And every time, and if you like, you could label each of those dots by a position. It's supposed to represent the insertion of a source at some position, x. And then every time I have a propagator, that's a line. And the lines connect dots. And those endpoints are associated with the positions x and y. So this generating function could then be very succinctly written in terms of this diagrammatic notation. And if you like, you could really even expand this out. So what is this? Well, the exponential of something is 1 plus that something plus 1 over 2 factorial times that something squared and so on and so forth. And indeed, for example, it is this something squared that gives us all of the various Witt contractions for the 4-point function of a free quantum field theory. So I didn't quite have a chance to get to it today, but when we introduce interactions, all that will happen is that we will end up with a more complicated diagrammatic set of rules for describing this generating function in terms of these diagrams. So in particular, the rule that we have here, so these would be the rules for constructing the Feynman diagrams of a free quantum field theory, say that the generating function is constructed by summing over all possible diagrams that you could write down, with the rule that a diagram has to be constructed by connecting dots together with lines And the dots and lines are connected in a very simple, are constructed in a very simple way. Each dot is connected by 2 lines. So that's it. The Feynman rules of this free theory are really not very complicated. But, for example, as we will derive on Thursday, for an interacting Feynman theory, such as a phi cubed theory, we have new sorts of diagrams or new sorts of ingredients that we can use to construct these diagrams. In particular, in a phi cubed theory, we'll discover a trivalent vertex. And so that when we construct this partition function, we will sum over all diagrams that you could construct by gluing together propagators and vertices and external sources just by connecting up various dots and lines using these trivalent vertices. So, for example, you would get something like that. In fact, it's only about a 10 or 15 minute argument to introduce that from here. I'm out of time, so I don't want to go through it right now. We'll do it when we're fresh next time. So maybe I should just stop here, but before I do, let me see if there are any questions. So we've derived the Feynman rules for a very simple theory. We want to compute a correlation function. In a free quantum field theory, you just connect dots with lines, with the simple rule that each dot can have 1 line coming from out it, and every line needs to end on 2 dots. Any questions? Maybe just to set the stage, what we're introducing here are what are known as Feynman diagrams in position space, because we're calculating correlation functions of these field operators at different locations, different positions. It turns out that at the end of the day, Feynman diagrams are much easier to think about in momentum space than in position space. So the Feynman diagram technology that we'll be introducing now is actually a little bit more difficult to compute with than the Feynman diagram technology that we'll be using at the end of the day when we compute, say, scattering processes in quantum field theory. Yes, question?
We were using this Fourier transform to go with that operator.
Yep.
And then we use it for doing the integral.
Mm-hmm.
Can you please go over it? Just
The Fourier transform?
Because I didn't catch how we use it.
Good. Okay.
That's from after,
Right.
after using this
Yeah.
transfer.
I mean, the point really is that you have this kinetic term where you integrate over phi, where you integrate this complicated operator. The point is that that operator really looks much simpler in Fourier space. It's just a function of k, okay, as opposed to being a complicated differential operator. This is why, right? This is why we study Fourier space. D by dx just becomes a number k, right, rather than an operator. That's what Fourier space does for a living. And so the partition function then became a very simple integral when we did this. Rather than a functional integral, it became a product. So a functional integral is a product of a bunch of one-dimensional integrals. The same way that any multivariable integral is a product of a bunch of one-dimensional integrals. The question is, how complicated is the integrand? So when you think about a path integral in position space, the integrand is very complicated. It's like, it connects phi of x with phi of x plus epsilon, right? Because that's what a derivative is defined to do. But when you think about it in momentum space, the integrand is very simple. It just takes phi of k here, say, and multiplies it by some function of k. And so that means that if you think about the integral, not overall paths, that the overall field configurations in physical space, but overall field configurations in momentum space. So here, literally what I'm doing here is rather than integrating over the value of the field at a bunch of different positions and multiplying that together, I'm integrating over the value, the Fourier transformed value of the field at a bunch of different momenta and multiplying over momenta.
And the step below it.
Yes.
So
I'm just doing a change of variables of a one-dimensional integral.
yeah, and then
So going from this step to this step, what do you do? Just take this, just plug it in. Okay. Right. And what do you get? You get this term here. You get some terms that are linear in chi, but I've chosen this coefficient. I've chosen that denominator here precisely so that they cancel.
then we have the c 0, 0.
Mhm.
Below we just there is
Yeah. So what did I do here?
We have the propagator here,
Yeah.
and we get rid of exponentials. It was kind of accurate.
There's no. Yeah. All I've done so you understand the derivation of this step? All I've done in going to this step is I've inserted this definition of J here. Right? So this guy becomes the integral dx. This guy gives you an integral dy. And then you get this integral d4k becomes this integral d4k. You get two integrals of e to the I kx and e to the I ky, which give you these things here. That term here went down here, and then I think that's it, except for possible minus sign mistakes. Yeah. It is possible I made a minus sign mistake somewhere. It does happen, believe it or not. Good. Is this more or less clear? Yeah. Great. Okay, good. See you on Thursday.